topic, but we have more or less covered whatever we wanted to cover. That took more time than expected. So, the other part of the course, which was there at one time when there were 4 classes to this semester, per week to this course, of course, has to be curtailed drastically. And so, what I am going to do is deviate firstly from the syllabus. The syllabus is principle of virtual work as a way of introducing the Lagrangians and then going on from there to Hamiltonians and so on. One reason why I will not do it is that it takes some time to do it. I don't have that kind of time left in the semester. And the other is, any one of you who is going to go on to take a physics course in classical mechanics will have a very detailed treatment of that in the 3rd year first semester course. So, no. So, as I was saying, because you are going to learn the principle of virtual work in great detail in the 3rd year first semester course, I am going to take a different approach for 2 reasons. A, it's quicker. B, it's also a very, very important part of all of physics, indeed all of science perhaps. And so we are going to talk about the Lagrangian and the Hamiltonian dynamics from what is called the variational approach. That, of course, that in itself is a huge topic again. However, I am going to introduce you to the very basic idea here, and I am going to do something which may sound a bit, ill-motivated to begin with. The advantage of starting with the virtual work principle would be that you start with Newton's laws, then show that there is a principle called the virtual work principle, first establish that, and using that end up showing that the differential equations that are obeyed by some function called the Lagrangian can reproduce the entire Newton's laws without having to worry about something called the forces of constraint. So at least maybe I should at least tell you what that issue is. And for that, let me just take an example. You have a pendulum swinging in a plane. How many coordinates do you need to describe it? X and Y is moving in one plane, right? But X and Y, suppose I measure X from here and Y from here, then X and Y are not independent coordinates, right? If it's a pendulum with a length L in the form of mass M, then X square plus Y square is given by L square. So if you know X, you can figure out Y, right? So here you could use 2 coordinates, X and Y. It's a motion in a plane, so you would want to use 2 coordinates, but using X and Y is an overkill. You get too many things. You are trying to calculate too many things which you don't need to here. Any one of them would do. So you could say I could use just X and not use Y. But then Y is there in this equation. After all, the angle which the thread makes, which tells you what angle the forces are at, all of that will depend on both X and Y. So it becomes a bit complicated using X, but it's easier using the angle theta. Of course, if you know the angle theta, you know exactly where the particle is, right? So what is the situation here? You want to specify the configuration of your system, which means exactly where every part of your system is at a given instant. That's the configuration. With a single pendulum, the angle theta is enough to tell you where every part of the particle of your system is. If it were, say, something like a double pendulum, let's say, one pendulum from which another pendulum is being hung and the whole thing is being swung, how many coordinates would you need? Well, 4 if you wanted to specify the X and Y coordinates of both the particles. But again, you have 2 constraints, right? If this were this were at x1, y1 and this were at x2, y2, then the conditions would be x1 square plus y1 square is L1 square, where L1 is the length of this pendulum. A2 will be x2 minus x1 whole square plus y2 minus y1 whole square. Y2 minus y1 whole square would be L2 square. So although you do have 4 coordinates, there are 2 constraints, which means you can make do with basically 2 independent things, right? And the 2 independent things that you need could be x1 and x2, but it's easier if you use theta 1 and theta 2. So these quantities which you use to specify the configuration, and in many situations you cannot avoid having constrained entities like these. Like sometimes you cannot avoid using coordinates like x and y, whether despite the fact that there is a constraint between them. But if you can avoid using dependent coordinates and just use independent ones, then you may have to resort to coordinates which are really not coordinates any longer, like theta. Of course, it's not what you would usually call a coordinate. Theta is a angle is dimensionless, x and y are dimensional, and so on. So things like theta out here, or theta 1 and theta 2 in this problem, these are called generalized coordinates. Okay. And very often when you are dealing with systems with constraints, it's actually easier to use generalized coordinates than the familiar Cartesian coordinates. Now in this case, the generalized coordinates are very easy to combine. In other more complicated systems, it may be more difficult to figure out what kind of generalized coordinates you should use. Yeah.
When I am doing a pendulum, it is also important that I find out at which plane.
Yeah, so I am assuming that it's moving in a plane. If it were not moving in a plane, you would need 3 coordinates, x, y, z. Even then there would be one constraint, x square plus y square plus z square would be L square. So you would need 2 parameters, 2 independent parameters, and that could be theta and phi. So when we say pendulum here, we mean simple pendulum, something which is oscillating in a plane. Of course, the double pendulum would mean 6 coordinates, x1, y1, z1, x2, y2, z2. But again, it would have 2 constraints. So basically, 4 independent parameters would work. Now, do you have to use angles? The answer is no. You could use other things as well. Depending on your system, you may be in a position where you would use one one coordinate, which is a length, another coordinate, which is an angle. Could be something more complicated. Yeah.
So what is the constraint basically you are talking about?
Constraint is anything. Constraint essentially means anything which forces things not to be independent. X and y for a pendulum, they can't be given independent values, right? X square plus y square has to be L square. That's called an equation of constraint, a restriction. X1 square plus y1 square equals L1 square, x2 minus x1 whole square plus y2 minus y1 whole square equals L2 square. These are equations of constraint, restrictions on the possible values which the coordinates can have. Yeah.
So you said that we can use other parameters other than theta 1 and theta 2. So how are we exactly defining generalized coordinates?
Any set of entities which, when specified, completely specifies your configuration. Right? That's it. Your generalized coordinates essentially means a method by which you can specify, or a set of numbers or set of entities which, when completely given, specifies the configuration of a system. That means where everything is at each moment. Of course, not the motion of the system. The motion would need not only the positions, but how fast these positions are changing. So in addition to generalized coordinates, you would also need generalized velocities. So in the case of the pendulum, generalized coordinate would be theta. The generalized velocity would be theta dot, d theta d. Similarly for the double pendulum, theta 1 dot, theta 2 dot. These are the generalized velocities. Coordinates tell you where everything is in your system. The velocities will tell you how the things change with time. Okay? Now, suppose I were to try to solve this problem using Newton's law. You know how. You have all done that, right? But what do? You have forces. What are the forces acting on the pendulum? You have the weight mg, which you know exactly how much it is, right? Of course, in this case, it's very, very simple. Mg is a constant, uniform force, always vertically downwards and so on. But that's just a special situation, right? It could be a more complicated force, but I know the force completely, right? The position of the particle and perhaps its velocity at most, if it were a magnetic force, would be enough to tell you what the force is. In this case, of course, there's only mg, which is downwards. The other force T, that is a problem. It's not a problem because it's variable. If mg had not been constant, but something which varies its position, that might have made this particular mathematical problem difficult to solve, but would not have added anything to conceptual difficulties. The tension in the string has a different issue altogether. Can you tell me how much is the tension in the string at this angle? mg? mg cos theta? mg sin theta? So all kinds of trigonometric functions fluctuating in. I have checked it here.
Like t cos theta could have been, sir.
Well, actually, no, you cannot tell me. Now, you are assuming that the thing is stationary here, right? It has to be stationary, you have to hold it here with some other force. Okay, so anybody who is giving me t in terms of mg would not be able to tell me what it is because it will depend on how much force I am applying to hold it stationary. Do you expect a pendulum to be there and just stay there without anybody else doing anything?
It would be instantaneously stationary.
Did I say that? There is just a pendulum moving in its path somewhere. Okay, now that you know it's somewhere in the middle of its motion, can you tell me what t is? No, it's not. T is not a function of theta, it's not a function of theta dot either. No, it's not a function of theta and theta dot. I'm pretty sure everybody has solved this problem. So basically what you have to do is this. T minus mg cos theta is going to be the force along this line. How much is that? That is ml theta dot square. But that depends on the motion. Now what is theta dot? That's not specific. So is the t a theta dot dependent thing? That's not the case. The case is t depends on how the thing is moving. Okay. The important point is tension is not a force which can specify that this is going to be this. You put it somewhere, this is the tension. You can't say that. The tension will depend on. So, why am I saying it's not a function of theta dot in that sense? Move the particle to some other initial position, make it go. It will go to the same point with an entirely different velocity, will have an entirely different tension. Right? Tension depends on the result that what are you trying to do? You're trying to calculate the motion, right? The force of tension depends on the motion itself. Why? Because tension is a force of constraint. It's something which is there to maintain that x square plus y square is l square. If the tension had not been there, what would have happened? So the particle would have dropped straight down. The length being constant would not have worked, right? The force of tension, it takes whatever value it needs to take to keep the constraint intact. Okay, so this was a particularly simple problem where you could solve the problem by other means and then go back and calculate the force of tension if you needed to. However, the force of tension itself cannot be put in as an input to the problem. Usually when we talk about Newton's second law, it's mass into acceleration equal to force. Force is something I know from somewhere else. That tells me the acceleration. Here, that's not the case. Any force of constraint will adjust itself to take the value which is necessary to maintain that constraint, right? And therefore, you have to solve for the motion first, and from that you can figure out the tension if you wanted to. Okay? So, using the traditional Newtonian way has two big issues. One is very often you would have to deal with more coordinates like x and y. Here. You could write the MA equal to F equation as nx double dot equal to something, ny double dot equal to something. then solve them, keeping in mind that x and y are not independent, but you have x square plus y square equals x square. There's a lot of work. Also, those equations, mx double dot and my double dot, has the tension inbuilt in it, and the tension, the force of constraint, is not known a priori. It comes out of the solution of the equation of motion. So typically, whenever you have constraints, the standard Newtonian method does not fail. It just becomes difficult to use. Okay. So one advantage of the Lagrangian approach is basically it helps you to get rid of forces of constraint in most situations. Okay. At least it helps you to write an equation where you can ignore the forces of constraints completely. Well, not always, but very often, in most situations. So all these exceptions to what I'm going to say are going to be very much part of your third year first semester course. Okay? But in most situations, the Lagrangian approach, which will allow you to work without worrying about the force of constraints, which are actually unknowns in your problem. What you know are the constraints. You don't know how much force is being applied because of that. That lack of knowledge can be sort of ignored in the Lagrangian approach. In fact, the method of virtual work, principle of virtual work essentially establishes that. But having said that, let's not talk too much about that any longer. That would take me way too long. So, yeah. It is. Which is why you do not know how much it is unless you know how the body is moving. Friction wouldn't be. Friction is part of the force of constraint, but it's not entirely, its value cannot be reduced by exactly how the thing is moving. And in fact, okay, let me just also put a caveat here. The Lagrangian method works best when there is no friction. In fact, many authors will tell you it doesn't work at all if there's friction. That's not really true. You can actually modify the method to account for friction, but it works best for conservative systems. So we will not bother about friction right now. Okay. So I am aware that there are many gaps in what I am saying, but those gaps are deliberate because way too little time. One more thing that we need to worry about is, not one more thing, we need to understand these idea about generalized coordinates and their number, which is what you call degrees of freedom. By the way, that's a term which should be familiar to all of you, right? Degrees of freedom simply means how many independent numbers do you need to specify the position of a system. So, simple example, this chalk which you can think of as a straight line. Let's imagine this is a straight line. How many degrees of freedom does this have? It is moving through three-dimensional space. 3?
6.
No, this can move anyway.
6.
You want to specify its configuration at any given instant. 5. Why 5?
Yeah, 5.
Why not 6? Why not 10? Okay, you might say if I specify this endpoint and the other endpoint, that's okay? That's enough? Right? I am assuming for the time being that you can imagine that this chalk is a line. It's not, it has a thickness. Let's ignore that for the time being. Suppose this were really a line of fixed length. Then if you tell me what its two endpoints are, you have completely specified its configuration. Right? Where it is at this given instant. To give the two endpoints, how many numbers would you need? 6. But there's one constrained equation, right? x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square will be L square. So you need actually 5. How do you pick out the 5? There are many ways of picking out the 5. You could give me x1, y1, z1, x2, y2, allow me to pick out z2 from there. Of course, z2 will come out only up to a sign, but it is locally. So the same x1, y1, z1, x2, the same position for this, same x1, y1 for this, could be either this or this. Right? Same x1, y1, but opposite z's. That's possible, but that's for the time being. We can say that at least locally, if you know where this is, at the next instant it's not going to flip over, right? It's going to be close to it. And if locally you will be able to specify the configuration by just using x1, y1, z1, x2, y2. Of course, there are many other, you could have 65 possible, that is 6 possible ways of doing this, right? You could drop x1, you could drop y1, use that rest. That's not the most convenient thing to do. A more convenient thing to do would be perhaps to give the center of mass, which needs 3 numbers, and then about the center of mass this can only rotate. And for the rotation of the line, you can give two angles. That's usually more convenient. But more convenient doesn't mean that that's the only possibility. There are multiple ways of assigning generalized coordinates for the same system. One may be more convenient than another, and in fact, even for the same system, depending on the problem you want to solve, one choice of generalized coordinates may be more convenient than another. And in another situation, the other choice may be more convenient. Now, so let's quickly do this. Let's say we have 2 particles moving in a plane, completely independently. How many degrees of freedom? No, in a plane. 4, right? 2 each. 2 particles joined by a rigid line. 3. 3 particles forming a rigid triangle. 3. Why? 6 coordinates, 3 constraints. Now we have 4. So let's see. 6 is just twice n, right? 2 degrees of freedom, 2 coordinates per particle. If an n particles, 2n. And constraints are how many lengths you have. How many lengths you have is how many pairs, right? So how many pairs can you form out of n particles? NC2. Which of course works here. This is 2 times 3 minus, right? 3. Okay, 4 particles. Let's just use this formula. What does it tell you? N equals 4. That is, you have some kind of rigid body. Now, of course, how many distances do you have? With 4 particles, how many distances do you have? 6 actually. Just specifying the edges doesn't tell you what the thing is like, right? You just specify the edges, the thing could squish. You also need the diagonals. So 6 distances, 4 particles, how many numbers? What is the number here? 2. Now, you should realize that there's something wrong with that. To specify position of 3 particles, it takes you 3 numbers. In a plane, it takes you 3 numbers. To specify the position of 4, it takes you 2. Why is that a problem? Of course, you may say more particles, you should necessarily need more numbers. That seems intuitive, but that's not a proof.
So, can't you do it with just 3?
Yeah, I can do it with 3, but do I need to do
No,
it
I'm
with
saying can't you just do it with 3 conditions?
You can't do it with 3 conditions. That's
Just the
actually wrong.
length of the diagonals and the angle between 3.
Length of diagonal and the.
3 constraints, length of the both diagonals and the angle between them.
Will that completely fix the thing?
No, because you don't know the intersection point of the diagonals are.
So length of the diagonal, if you knew where the diagonals intersected, then the length of the diagonal angle between them would tell you exactly where the things are.
Yes, correct.
But then you have to tell me where the thing is. So how many do you really need? But he is on to something. In fact, if you continued this, you would be in a disaster very soon. Because with 6 particles, 8C2 is, okay, twice 6 is 12. What's NC2? 6C2? 15, right? So I've ended up with 15 conditions with 12 coordinates. So minus 3 number of coordinates you need. Or with 5 you need 0 actually. Right? If this formula were correct, with 5 you would need exactly 0 parameters to specify the system. What would that mean? That if they were correct, that would mean that if you have a collection of 5 particles rigidly connected to each other, you have no choice about where it would be. Because 0 coordinates need to specify. The moment something comes with 5 particles tied to each other, they are fixed forever. You have no handle on that at all. That of course is absurd.
So, should we use something like
Now, first of all, let me just ask you one thing. Why is it a problem that 4 particles need less coordinates, apparently, than 3 do. Why is this at all a problem?
Because you need lesser coordinates to show congruence. For instance, instead of just saying
Congruence. Again, please come down to synthetics.
So if you can say, if you are saying 3 constraints being S, side, and side.
Again, those are constraints for triangles. Please don't.
Like
For quadrilaterals, things are more complicated.
Yeah, so we are just extrapolating that. So instead of using side, and side, we can use angle, side, and angle.
That's all. That's still 3.
But for quadrilateral, instead of using 6 constraints,
Again, I'm sure you're going to get to the right answer about why the quadrilateral doesn't really need 2. I'm not asking you that at all. I'm asking what is wrong with the quadrilateral needing 2 where the triangle is like 3.
So if we have there are 4 points and there are 2n coordinates. If we have 8 coordinates, then we also have the distances between 2 of them, right? So
Again, you are trying to answer why this 2 is wrong. I'm not asking you that right now. Let's see whether you can understand the logical question first. What is logically wrong with a quadrilateral needing 2?
Because
I'm not talking of how many quadrilaterals need. So don't give. Remember, the problem is you are not attacking the question. You are trying to answer why. What is the right answer for the quadrilateral?
you're taking more constraints than we actually.
Why is there a problem?
I mean, if you need just 2 constants for a quadrilateral, that means you know 4 of the points, and you can correct.
Exactly. The point is, if you needed 2 really for a quadrilateral, then 2 would have told you the quadrilateral, which means quadrilateral has 3 points in it, right?
So you know 3 points already.
You know 3 points already with 2 numbers. In fact, with a pentagon, you need 0 according to this, which means for everything you need 0.
Exactly.
Okay. The correct answer, of course, is that this count is wrong in the sense that it is right that you have calculated that there are 6 distances between 4 points. But these 6 distances are not independent distances. Okay? If you give me 5 of them for a quadrilateral, the 6th will be fixed. You need all 5. You need 4 sides and a diagonal, for example, to completely fix the quadrilateral. But once you have 4 sides and a diagonal, the other diagonal cannot be chosen arbitrarily. Okay. Let's think about the geometry of it. That should be clear. So let's do this for this large object, which we assume cannot bend, so it's rigid. How many parameters do you need to specify its position completely?
4.
It's moving in 3 dimensions.
So the object is 3 dimensional.
The object is 3 dimensional. It can move in 3 dimensions. It's made out of capital N number of particles, where capital N, if you think of the atoms, would be way more than the Avogadro number. Right? It is much more than 1 mole. So, how many parameters do you need to specify this? Assuming, of course, that this is completely rigid, which is not the case for a duster. So, okay, let's play a game with this. If I were to fix 1 point here, let's say this point, then how many numbers will that mean? 2. Again, you are moving in 3 dimensions. You can't specify 1 point with 2 numbers. 3. But if you fix this, does this fix the whole duster?
No, because you can rotate
The duster
it.
can move in many ways.
Yeah.
Okay, let's say I choose to fix another point. Let's say the other corner.
Rotate it around you can say rotate.
So how many numbers you need now to fix the other corner?
3 more.
No, 2 more. Because you know the distance between the 2 corners, right? You know, for this first point, you need 3 numbers. For second point, you don't need 3 numbers, right?
Yeah.
You need only 2, because this distance is known. Now that 2 points are fixed, does that fix the duster? So it can still turn around. But to figure out its exact configuration, you need to know how much it has turned. How many is turning around this line, right? Yeah.
I mean, if you have just 2 coordinates, can't it be the negative of the... Can't you take it in the other direction as well? So you need 3 coordinates in the end.
What?
So suppose you have the first
No,
3
no.
coordinates.
You mean this one and that one?
Yeah.
We have already said we are looking at this locally. We are not looking at this, a possible flip.
Cool.
You can do it without the, if you don't use Cartesian coordinates, you can specify this position exactly using angular coordinates. So 3 and 2 is fine, but for this further rotation,
2 more.
you need 1 more. Now the body can only rotate about this axis. And where it is exactly will depend on the angle through which it is rotated, only one more parameter. So 6 parameters will fix a perfectly rigid body in space, no matter how many particles it's made out of. Okay. So the number of degrees of freedom of a rigid body is 6. By the way, the degree of freedom word is badly abused in chemistry. So when I say badly abused, I mean that what they do is something like this. Say, you use okay, it's not only chemistry. It's also done in physics in the sense that when we do thermal physics very often, we do things like that. What is the number of degrees of freedom of a diatomic molecule? 5, 7,
5.
etc. Actually, the number of degrees of freedom is only 6. 6 if it's flexible. If it's rigid, if it is a fixed length thing, 5. If it's flexible, of course, with the length distance between the two ends, two atoms is not fixed, then of course you need 6 because you need to know where both are, right? So degree of freedom is actually 6. A thermal physics textbook and sometimes, and a chemistry textbook almost always will tell you that the degree of freedom is 7. That's really not a degree of freedom, that's an effective degree of freedom which you use to calculate the number of half kgs you get in the heat capacity calculation. Okay, that's a different thing altogether. It comes from this calculation, but it's not the same thing as this. Okay, so when you see things like there are 7 degrees of freedom for a diatomic molecule, that of course is rubbish, because to specify the 2 points of a diatomic molecule, you need just 6 numbers. You can't need more than 6, right? The 7 means something else. 7 means you have 5 degrees of translational degrees. Actually 3 translational, 2 rotational, that's the way you talk about it. And there's 1 vibrational degree, and the vibrational degree of freedom counts twice. Counts twice simply because when you're doing equipartition theorem to calculate the heat capacity and stuff like that, you take into account the fact that vibrational degree of freedom has not only kinetic energy but also potential energy. And it's an accident that potential energy for small vibrations also contributes the same amount on average as kinetic energy does. So you get a half kg for the vibrational degree of freedom extra. Okay, that is something that's not my topic at all. I just told you this so that you can you may not get confused with the number of degrees of freedom we are calculating here and the number of degrees of freedom you get to calculate when you say heat capacity of say diatomic molecule is something like this. Okay, now let's get to the actual topic today, which is variational method or something which is often slightly wrongly called slightly wrongly because it doesn't really have to be least action. Could be most action as well. But it's usually least. So the idea is the following. Idea is there's something called the action, which is either written as S or A from tradition. A makes sense, of course, A is the first letter of action. S must be German or something else, I've forgotten what it is. But S is often used. Okay? And what is this action? The action is something like this. There is an entity called the Lagrangian. I am not going to explain where I am going to get this from. I am going to tell you what it is at the end. But there is something called the Lagrangian which depends on the configuration, which means if you have n degrees of freedom, it depends on the n coordinates. Remember, these could be Cartesian coordinates or this would usually be generalized coordinates. And the corresponding velocities. You take this function, integrate this with respect to time from some initial time ti or let's take ti to tf, some final time tf. It can also depend on time, although very often it doesn't. It depends on time in rare situations where there are certain things which you are ignoring. But let's put that in.
Why not other derivatives of the generalized polynomial?
Why not other derivatives? The answer is simple. Because this will give you a second order differential equation for the quantities q's, and that's what happens almost all the time. Why not other higher derivatives? There are certain theories where you do have higher derivatives in Lagrangian, but those theories are rather artificial, and all those theories have what is called an instability. Those theories are not valid theories for physics. Most.
So Lagrangian is a function that we are.
Lagrangian is a function of coordinates, generalized coordinates and generalized velocities. What is this function? Well, I will not tell you what this function is for the same reason that when you write Newton's second law, you write mass into acceleration equal to force. You don't immediately ask what is the force. For a specific system, of course, you have to tell me what the force is. Mass into acceleration equal to force works in general without specifying what the precise force is. Depending on your system, you can define forces, and putting those in, you can solve for the motion, right? The situation is very similar here. The Lagrangian defines the system. Okay? So different systems have different Lagrangians. The most common form of Lagrangian that we have, which is not the only form by the way, but most common, and that's the one we are going to deal with most of the time, at least in point particle mechanics, the most common form of Lagrangian is this. Kinetic energy minus potential energy. That's the most common form, not the most general form. And there are many other situations where this form is completely different. And they are also very, very useful. In fact, the immense utility of this formalism is it works not only for point particle mechanics, it works almost everywhere. So it's a nearly universal formalism which works everywhere in classical physics and can be slightly modified to give you very important results even when you are dealing with quantum mechanics. Okay? Yeah. There is. Somewhere in the Lagrangian there will be the mass.
We are not putting it as an input.
It's not. It is an input depending on the system. Mass is not there. Mass is a parameter which depends on the system. Right?
It's not only the
Right now, look, in the Lagrangian there will be many other, apart from the coordinates and velocities, there could be many other things. Okay? But those things are not things you are focusing on. Those don't change with the motion. Now, before we go any further, what kind of if you want to calculate this, can you actually calculate this at all without, if I just gave you this thing to calculate? What do you need to know to be able to calculate this? No, suppose I told you what the Lagrangian, let's say I have given you the Lagrangian. Let's say L is half m q dot square minus half k q square. Let's say I have given you this. Can you calculate this integral? Let's say I have written this down, s equal to this. Half m. So the question about where was the m? The m is in the Lagrangian. In fact, it also has another parameter k for the time being. Minus half k q square. This is just a Lagrangian for a particular system. But the question is not what this particular Lagrangian stands for. The question is in general. At least let's look at this particular example. Can you calculate what the action is going to be? You need the dependence of? Do you need the dependence of both q and q dot on t or only q on t? Only q on t will do because q dot can be calculated. If you look how q depends on t, q dot can be calculated because of that. But that really means in order to evaluate this, it's not enough to know q. You need to know q as a function of t throughout. At least between ti and ts, you know exactly what q was at every point in between. Right? So in general, when you take a look at the action with multiple number of coordinates in the top line, if you want to calculate this, what would you want to know? Q1 as a function of t, Q2 as a function of t, all the way to Qn as a function of t. Right? If you give me these functions, I can return to you the value. And the value is, what kind of object is the value? This value is, what kind of an object is it? Is it a function? Is it a function? Is it a number? Is it something? It's a number. Right? So this S, via this mechanism of this integral being carried out and so on, takes in a function or multiple functions of t. The example that I have given takes in one function of t and returns to you a number. Right? Okay. So, in the language of mathematics, this is an example of a map. It maps functions to numbers. Right? Yeah? Now, there's another term that we often use for maps in mathematics.
Relation.
Do we call that them operators? What's the most common term we use for maps?
Relation.
Functions. Come on. Again. Operators are very special kind of maps, etc. Functions are by definition synonymous with maps. Right? Things which take an input from a domain produces an output in a range. Right? However, we cases and even most mathematicians also feel much more comfortable calling something a function if it takes a number, produces a number. Right? This one doesn't. It will not take in a number and produce a number. It takes in a whole function and produces number. Okay, it is actually a function in the standard definition of the word, but it is actually called something else. It's called a functional. A functional is simply something which takes in a whole function or multiple functions, as in this case, and produces a number out of it. Okay? Clear? So it's not nothing very magical. It just takes in a function. And there are other functionals possible. For example, suppose you have some thing which takes in a function of x and returns the value of f at 1. That's also an example of a functional, right? It takes in an input as a whole function. What is the output? A single number. So that's also an example of a functional. So is this. This is more complicated, at least, than that. But both are functionals in the sense that taking whole functions and produce numbers. Okay. Now, the principle of restriction essentially says this. Suppose you have a situation like this. At Ti, you know that your particle is at xi. I am doing this in one dimension with using x1 and x2 as coordinates. The general thing can be immediately written down, but there, of course, you will have to change the, instead of xi, you will have to write qi1, qi2 up to qin to know the initial configuration and the final configuration is known. Let's say we are, for the time being, dealing with a particle moving in one dimension where the generalized coordinate is simply x. It's not even generalized, it's just an ordinary coordinate. So let's say we know this much. At Ti is at xi, Ts is at xi. The question that we are addressing is, what is the path in between? How did the particle go from here to here? So x is a function of t. That's what we want to find out. Okay, let me just do one thing. Since I am going to use q throughout for generalized coordinates, let's use q. Okay, qi for the time just means xi, but in general it could mean theta I, for example, initial angle and final angle. So there will be some path the particle actually takes, right? Some function q of t in between. The claim is that if you take a nearby path, not this one, not the one which the particle actually takes, but something which is very close to it, something like, say, this one, So this dashed line is a path which should be infinitesimally close to this one actually, but we can't draw an infinitesimally close path, so I am drawing a largely displaced path with one condition: initial point, final point is the same. So if you consider not only this one path but many other paths which are close to the original, to the actual classical path, but slightly deviating from that, while not deviating at the endpoints at all. Okay? The principle says that among all these paths, the action will be least when you calculate it for the classical path, for the actual path taken. The actual path the system takes. The system actually takes this particular path which are drawn with a solid line. You take nearby paths, any number, any one of them, right? Any nearby path, as long as the nearby paths all start and end at the same point or same configuration in general. The actual path taken will be the one which minimizes the value for the action, or to be more precise, extremizes the value of the action. Minimizes is what happens most of the time. Extremizes is the more general statement. Okay, so you have all seen a similar result. For example, if you have a source of light here and somebody looking at a mirror from here, there are infinitely many possible paths which light could have taken from here to here. Okay. In fact, the path could have been like this for all you care. But the path isn't like this, right? The actual path taken by light is straight. Okay, the shortest possible path is this one. For the time being, let's think of a situation where light is bounced from the mirror. Then, among all possible paths, the path actually taken is the path which takes the least time, right? There's a Fermat principle for least time. You all know this? And using that, you can prove that the angle of incidence will be equal to angle of reflection. That's simple geometry. You've all done this sometime or the other, right? Also, suppose this is a point from which light has traveled to this point, and you have two different speeds, media, so you have c and some other velocity v here. In order to go from here to here, light of course doesn't go straight. It goes like this, bending towards the normal that is entering into a medium with lower velocity. That way it spends more distance in the faster medium, less distance in the slower medium, and does it exactly in such a way that the time taken is the least. Of course, that if you use the time taken as the least criterion, class achieved, for instance. So, if you use the time taken as the least criterion, you can prove sin I by sin r will be C over V. Okay? Yeah.
So this seems like sort of like a circular argument, like, so if
There is no argument. I didn't give an argument at all.
like what I'm saying is if the endpoint is specified and when we are saying infinitely closer paths, we are already assuming we know the path it actually takes, right?
No, we are not assuming that we know the path it actually took. We are assuming that there is a path it will actually take.
Then how do we define closer? Like what is it?
So, of course, you could think of paths like this as well. But among all paths that you take, okay, let me answer that question to you in a slightly different way. If you have a function of a single variable, function, not a functional, how do you find out where is the minimum? Differentiate. Okay, it assumes differentiability in the first place, so let's assume, for the sake of our argument, that it's known to be differentiable. Then what do? You differentiate, then you get it to 0. Right? Why does it work?
Because
There's like a graph, then this is low.
Okay, there's a graph. At the bottom, the slope looks flat. Right?
Prove an infinitesimal from that minima. You haven't changed the value by a lot. So the derivative.
Okay, but you have not changed the value by a lot. Why So what does the minimum mean? Minimum means when you move away from that point, the value should go up. Right?
If it was previously changing and then it is changing in a different way. So by the
Yeah, but what is the precise argument why? Suppose I say that the slope here is not 0, but some other value. Say positive. If the slope is positive, it's going to go up, right?
then move down the slope, you should reach a lower point, right? But it's the minimum.
How do you mean going down the slope?
Meaning,
The slope is positive. What is going down the slope?
slope is the direction of increase, right?
Right?
Negative of the slope is the direction of decrease.
Okay. Essentially, I guess what you're saying is what I wanted to say, but I think you're using a language which makes it a bit more confusing for me at least.
That's why I said move down the slope.
Basically, if you go to the right, when the slope is positive, you go to the right, the function rises.
Yeah, so
But if you go to the left, the function drops. If it's a minimum, you don't want it to drop in either direction. So the slope cannot be positive. Slope cannot be negative either, because if it is negative, when you go to the left, it rises. Fine. But you go to the right, it drops. The only possibility has to be flat. Okay? So basically what you do here is exactly the same thing. You vary the path a little, see whether the action is changing. If it changes slightly, if it's, you may say, okay, fine, if I say this is a path, this is a possible path, not the classical path. And there's a path which you get by varying this. And you see that the action has gone up when you go from the lower curve to the previous one. Going up, that might seem like very good because you want the minimum, right? If it has gone up, that makes this curve, the curve I drew here, a perfectly nice candidate for a minimum action. However, you don't have to go up, change in this direction, and you can also change exactly oppositely in the other direction. And if you are going up when you are going around this, you will definitely go down when you go around this. Yeah.
So, but won't the work done on all these parts be?
First of all, work.
Yeah.
Who cares about work? What has work got to do with it?
Conservation of energy. So.
First of all, I'm not talking of work at all. I'm talking
talking of work.
Why are you talking of
Won't the work done on all these parts be the same? So it shouldn't have any. Why does this work? Why does principle of least action work? Like it's nice to hear it as it works, but why does it work?
Prove that it works.
Why? What is a more fundamental?
That this is the most fundamental you can get. You can't, okay, one way would be to argue that you cannot prove the principle of least action because that's that's the source from which everything else can be proven. The other one would be, if you were to believe in Newton's laws and constraint forces, that's the one we are not doing, remember, variational principle of least action can be derived out of principle of virtual work. Third year, first semester. 2 weeks of classes will be needed to establish that completely. So I'm not going to talk about that because frankly that is really not very useful because that will only explain why principle of least action works for mechanical systems of a certain kind. It will not be able to explain why it works, say, for electromagnetic fields, why it works for photon fields or say Higgs boson fields, for example. Okay? This principle is universal, way more universal than using it only for Newton's laws. So proving it starting from Newton's laws is essential in class if you were to only talk of classical mechanics. However, it's much better to assume that this works and start from this principle and from there show that Newton's laws will emerge. In the special situation, we will choose the Lagrangian to be the right kind. You choose the Lagrangian to be some other kind, you can get Maxwell's equations out of this. Same principle.
So how do you know how to choose the Lagrangian?
How do you know how to find out the force for a particular system?
Exactly. See, like you said.
How do you find out the force for a particular system? Do you find it by pure thought? Experiment. Everything ultimately boils down to that.
But you said like how we can't actually find the tension just by looking at the equation and substituting it back. So aren't you doing the same thing with the Lagrangian?
No, we are doing something much more fundamental. We are saying the Lagrangian defines the system for us. And then what is the system? Lagrangian defines the system. Principle of action tells you how the coordinates we describe the system change. Now, you want to figure out what will happen for a specific system? Of course, the specific system will have a distinct Lagrangian which depends on it. If that had not happened, the trouble is, this aim that you seem to have, that we all seem to have, of trying to unify everything and trying to understand everything in one feature, has this basic problem, and the world would have been a very dull place. If the Lagrangian could have been figured out from pure thought, then the world, everything in the universe would have behaved similarly, right? They don't. Why don't they behave similarly? Because different systems have different Lagrangians. So this, I admit that this comes as quite a shock when you first see this, because this is a very unusual way of thinking about things. But it turns out that this is way more lucrative in the end. It gives you a lot more. Yeah.
Sir, so given an arbitrary system in practice, how do you go about finding the Lagrangian?
You typically look at certain features. For example, in classical mechanics, we have this rather nice prescription that you take that if it's a conservative system, take its kinetic energy, take its potential energy, subtract that. Why do we take that? Because that will make the Lagrangian or make the principle of least action reproduce Newton's laws for you.
But that is only for conservative systems, right?
Only for conservative systems. If the system is not conservative, very often you can't use the Lagrangian method. Okay? So Lagrangian method is very powerful, but it's not something you can use everywhere. However, there are other situations where you can work back. Again, start from experiments, work back and figure out what the action is going to be. Much more importantly, in many situations we do same thing. You know the Lagrangian, you know the action, right? If you know action for all paths, you essentially know the Lagrangian.
No, if we know the Lagrangian for every path,
If you know you don't know Lagrangian for paths. The Lagrangian depends on q's and q dots, right? Given the path, this gives you the action. If you change the path slightly, you can find out what if you know the action for every path, that's the same thing as knowing. Basically, it's the same thing as saying if you know the integral of a function for any arbitrary endpoint, you know the function. Basically, the function can be found out as a derivative. Let's just change the output a bit. Now, let's come back to the. Okay, I don't have time today, so I will. This is just the basic outline of what we are going to do. So we will have essentially 2.5. So next week, 8:30 will be the class. 8 to 8:30 will be tutorial, of course. But the class will start at 8:30. Yes, there will be one sometime. 8 to 8:30 will be a tutorial. Now what that will be, I don't know. By the way, it doesn't have to be during class hours. Right?